Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this course on gas turbines and jet engines. So, today is lecture 21, which is the first lecture of week 5 of this course. Okay. So, today we are going to study the effects of mechanical losses, fuel addition and combustion inefficiency in real gas turbines. So, as compared to ideal gas turbines, what are the effect of these phenomena in real gas turbines. So, concept which will be covered till now for real gas turbines, what we have covered? We have considered the effect of kinetic energy, effect of irreversibility in a lot of detail. We considered that this is one of the most important effects. So, we considered isentropic and polytropic efficiencies. Then effect of pressure losses in the last class, effect of regenerator losses and variation of Cp and gamma. By including all these effects in our calculation, we can do the analysis of real cycle much more accurately. Okay. So, today we will complete this part by considering the 3 remaining effects, which is the effect of mechanical losses, okay, or frictional losses between mechanical parts. Then the change in mass flow rate. So, this is not a loss, but this is the change that needs to be incorporated in the calculation due to change in the mass flow rate, which occurs because of fuel addition. And finally, we will also consider that combustion may not be fully complete. So, there can be slight inefficiency. So, what is the effect of that, how to incorporate that into our calculations. Okay. So, we start with the first of these 3, which is the effect of mechanical losses. Now, what are the effects? So, why these mechanical losses are present? So, these are different from the irreversibilities which we had considered already for the turbine and the compressor, and this is also different from the pressure drops, the losses due to pressure drop in the regenerator and in the combustion chamber. So, these are losses which happens while transmitting power. So, for example, the turbine is transmitting power through the shaft to the compressor. So, there is a slight loss due to bearing frictions. Okay. So, that comes under mechanical loss, and then there are also windage losses which occur because of relative motion between the rotating parts and the static parts in the presence of air or gases. So, when air or gas is there and then one part is moving, rotating at high speed, the other part is fixed. So, that creates a drag and creates a frictional loss. Okay. So, these amount in total to a very small value, less than 1% of the compressor work input or about 1%, and to quantify this we define a parameter called transmission efficiency or mechanical efficiency. Okay. Mechanical efficiency or transmission efficiency, this will be used to quantify how much are these losses. Okay. We also need to remember that there are other equipments, okay, which are not directly part of the cycle or not the major components, but still they are necessary components. These are like auxiliary equipment like fuel pump, oil pump. Okay. So, all these are present for fuel injection. So, oil pumps are there for lubrication, so things like that. So, there are minor losses in terms of say power required to run this auxiliary equipment also. Okay. So, we will quickly define this mechanical efficiency and we will see how it is related. So, mechanical or transmission efficiency. So, if we let us draw a schematic of a turbine and a compressor connected together. So, this is a turbine and this is a compressor mounted on the same shaft. Of course, they need to be supported by bearings. Compressor, this is a turbine. This is rotating. The work output from the turbine, let us say this is equal to WT. So, a slight decrease of this work output, a slightly reduced amount of this work output is available to the compressor for running the compressor. So, amount of work output is WT. If we consider that the entire work output is used for running the compressor, we will need slightly higher work output as compared to the compressor work to run the device. Okay. So, this can be defined as, so what will be the best way? So, let us define it in another way, okay, because otherwise there will be confusion. Let us say that what is the work needed for running the compressor, WC. So, the work which is needed for running the compressor, this is equal to Cp of air into T02 minus T01 for a standard process. For a standard process going from 01 to 02 compression process. Cpa T02 minus T01 per unit mass flow rate of air. Now, the actual work that needs to be supplied from the turbine will be slightly higher. Okay. So, that work which is needed, so WTC, the work that is supplied from the turbine for the compressor, that needs to be equal to Cpa T02 minus T01 divided by this efficiency or the mechanical efficiency, or the other way around, if the turbine is supplying WTC amount of work. So, for running the compressor we have, this is WC which is Cp T02 minus T01. For running the compressor we get efficiency multiplied by the work which was originally supplied by the turbine towards the compressor. So, this value of mechanical efficiency is very high, of the order of 0.99, okay, because the losses for large devices, the frictional losses are very small compared to the work required for running the compressor. So, using this we can take into consideration how much work will be needed by the turbine to run the compressor, and accordingly we can do the calculation based on this equation. Okay. So, next effect which we need to consider, it is not a loss, but it is effect due to the variation of mass flow rate. Why this mass flow rate is varying? So, mass flow rate initially is equal to the mass flow rate of air at the intake, right. So, I have, let us say, this is 01, 02. So, at the intake we have a mass flow rate m dot A. Now, during the conversion we are adding fuel. So, there is fuel injection. So, while injecting fuel the mass flow rate will increase. Let us say that the fuel injection mass flow rate is given by m dot F, okay, mass flow rate of fuel. And m dot A, which we have already considered before, is the mass flow rate of air. So, for calculation related to the turbine, now we have to consider this new mass flow rate, which is the sum of the mass flow rate of air plus mass flow rate of fuel. Okay. So, So, this is the resultant mass flow rate. So, this needs to be incorporated in our calculation. Similarly, during the combustion process, the calculation needs to consider that initial energy was based on a mass flow rate of m dot A, but the final energy or the increase which has occurred, in that case the mass flow rate is m dot A plus m dot F. We will see how to consider this combustion chamber effect later on. For the turbine, it is directly we just add the both mass flow rates and we take into we do the calculation in terms of unit mass flow rate of air for the entire cycle. Okay. So, for example, for turbine work per unit mass flow rate of air in the entire cycle. So, per unit mass flow rate of air, this is defined in terms of the intake mass flow rate of air the turbine work. If it is WT, then this is equal to the overall turbine power output divided by the mass flow rate of air, okay, where this WT will be in terms of mass flow rate of air plus mass flow rate of gas fuel, sorry, m dot A plus m dot F, Cp of gas. In this case, this is temperature difference is T03 minus T04, this divided by m dot A. The numerator, this top part is equal to the power output of the turbine. So, this is comes out to be equal to 1 plus F, where we define F as a parameter called fuel air ratio, ratio of the mass flow rate of fuel to the mass flow rate of air. So, 1 plus F Cpg T03 minus T04. Okay. So, per unit mass flow rate of air, the mass flow rate in the turbine is 1 plus F, not 1. Okay. So, 1 plus F, where F is known as fuel air ratio. So, this is the ratio of mass flow rate of the fuel to the air. For gas turbines, we use a very lean mixture. Okay, later we will discuss this. So, for hydrocarbons, this stoichiometric ratio will be somewhere between say around 15, so between 10 to 20, which means that the mass flow rate of air which is required for complete combustion is equal to around 15 to 20 times of the mass flow rate of fuel. We can calculate the exact value based on the exact say formula of the fuel. Okay. But for gas turbines, we use a very lean mixture to keep the final temperature low at the turbine inlet. So, typically fuel air ratio, air fuel ratios of the order of 50:1 is used, okay, or fuel air ratio of the order of 1/50 is used. So, this ensures that the temperature at the exit of the combustion chamber is relatively low, so that the turbine blades do not fail. Okay. So, this we can calculate as we will see later from combustion chamber calculations doing energy balance, and this additional mass flow rate needs to be accounted for in the calculations. Okay. So, calculations done per unit mass flow rate of air at the intake. Okay. For that, the increase in mass flow rate needs to be quantified using fuel air ratio. Okay. Fuel air ratio is F. So, air fuel ratio will be 1 by F, and we have discussed that very high air to fuel ratios are used, very high air fuel ratios are used of the order of 50, so that the maximum temperatures are limited and the turbine blade material limit is satisfied. Okay. So, now we move to the last point. Okay. Last point is, although it has very minor effect, but still it should be considered, which is the effect of incomplete combustion or inefficient combustion. Okay. So, for example, combustion proceeds everywhere, but at some small pockets or some locations the combustion is not fully complete. So, the entire amount of energy which could have been released from the fuel, the calorific value of the fuel, that is not used up properly. So, a slightly lower amount of energy is released. Okay. So, combustion losses may occur due to incomplete combustion. Incomplete combustion may occur if there are local regions where the flow velocity is not the flow velocity, the oxygen concentration is lower. This can also happen if the flow is too fast and the time that is needed for complete reaction is not available for the reaction to occur. Okay. If the process, if the flow is too fast, the combustion products will blow out before the complete combustion occurs. So, it can also happen in those cases. In this case, what happens for if there is incomplete combustion, the energy released is slightly lower and it also leads to formation of carbon monoxide instead of carbon dioxide if we have partial combustion, or if in the case that, which is very rare, that there is a lot of incomplete combustion, even unburned carbon particles can be there, but that is very rare, does not occur normally for gas turbines. So, these losses are quantified by using a efficiency, by defining an efficiency which is known as combustion efficiency. So, how is this defined? So, combustion efficiency is defined as the actual energy which is generated in the combustion chamber due to combustion, which is equal to mass flow rate of air plus mass flow rate of fuel. So, this is the total mass flow rate. Let us say that again we will just draw a quick diagram for reference. 1 to 2. So, when I say 1 to 2, so in all cases I am saying that actually these are stagnation states. So, I may omit saying the 0, but it is there, 02 to 03 and 03 to 04. So, 2 to 3 is the combustion process. So, at the exit of the combustion process, we have mass flow rate m dot a plus m dot f, and this energy can be written as Cpg multiplied by T03 minus at the inlet the energy was m dot a Cpa T02. Note the different Cp values, okay, because here it is air and at state 3 it is gas combustion product. So, this is the actual energy released divided by the theoretically maximum amount of energy which could have been released, which is equal to the mass flow rate of fuel into calorific value of fuel. What is calorific value of fuel? Calorific value is the energy which can be released by combustion of, by the complete combustion of 1 kg of the fuel. Okay. Per unit mass of the fuel, how much energy can be theoretically released? Okay. This is the calorific value. For typical hydrocarbons used in gas turbines, okay. So, gas turbines or jet engines, the fuel is near to kerosene in composition. Aviation fuel is used for jet engines, which is near to kerosene in composition. These calorific values are of the order of around 40 megajoule per kg or 40,000 kilojoule per kg. Okay. So, this can be simplified by cancelling the or by dividing both the top and the bottom by mass flow rate of air. So, this will be equal to 1 plus F Cp of gas T03 minus 1 into Cp of air T02 divided by F into calorific value QCV. Okay. So, by doing this energy balance, so if we do an energy balance and if the eta B is known, then we can find out what should be the mass flow rate of fuel if all the other variables are known. So, we will be using this type of relation for calculating the mass flow rate of fuel that is necessary based on the actual combustion efficiency and the calorific value and the actual temperature rise. So, this completes these 3 points. So, we have considered till now all the 8 points: effect of kinetic energy, effect of irreversibility in compressor and turbine, effect of pressure losses, effect of regenerator losses, variation of Cp and gamma. Then today we have considered effect of mechanical losses. We have considered that we define a transmission or mechanical efficiency. Then variation of mass flow rate due to fuel addition, which we have considered by defining a fuel air ratio, and effect of combustion efficiency, which we have considered by defining a combustion efficiency. Okay. Let us consider a very simple example again to illustrate this combustion chamber calculation. Okay. Combustion chamber calculation, exactly similar diagram to the last case. So, we will quickly redraw. You should practice also how to draw these things fast, because this is always needed for solving all problems. So, 01 to 02 compression, 02 to 03 combustion, and 03 to 04 expansion in the turbine. Our combustion process is 02 to 03, which is our concern in this problem. So, it is given that the inlet temperature to the combustion chamber, which is typically it is termed as the compressor delivery temperature. Okay, compressor delivery temperature is 600 Kelvin, and the turbine inlet temperature, which is the maximum temperature after combustion, this is 1500 Kelvin. So, this is what I was saying, that this temperature is regulated based on the maximum temperature which can be considered for continuous use in the turbine. So, and this can be regulated by controlling the how lean is the mixture of air and fuel. So, how lean is the fuel air ratio. Okay. So, anyway, and the combustion efficiency is known to be around 0.98. Typically, combustion efficiencies are very large, very high for gas turbines. It will be of the order of 98 to 99%, which is unlike means reciprocating engines. Reciprocating engines have significantly lower combustion efficiency, because there the chances of incomplete combustion is much higher. In these cases, because we are using a very lean mixture and the process is occurring at a steady state, in steady flow condition, the combustion occurs almost fully, and we get around 98 to 99% of the theoretical energy release. Okay. Calorific value in this case is given for the fuel, it is 40 megajoule per kg. So, all are realistic values. We need to find, the fuel air ratio that is needed to run this combustion chamber, and the amount of heat addition which occurs per unit mass flow rate of air at the intake. Okay. So, how do we do this? We again start with the energy balance. So, in all cases we should start from the energy balance. So, energy balance in the combustion chamber, the amount of energy which comes in the combustion chamber. So, this is equal to per unit mass flow rate, this is equal to F per unit mass flow rate, the mass flow rate of fuel is F into calorific value of the fuel plus 1 into CPA into, let us say that T02, and the energy which is at the exit of the combustion chamber. So, this is equal to, so this needs to be, this FQCV needs to be multiplied by combustion efficiency if the combustion is not 100% efficient. Okay. So, this is the actual amount of energy released, eta be FQCV plus the energy of the fluid per unit mass coming through the from the compressor. This should be equal to 1 plus F mass flow rate at the exit of the combustion chamber into Cp of gas into T03. Okay. This is the same expression as the previous one, but just written in a different arrangement. Okay. So, this we can write by taking all the F terms together, we can write this as eta B q C V minus Cpg T03 multiplied by F. So, this is equal to Cpg T03 into 1 minus Cpa T02 into 1. Okay. So, finally, we can see that the unknown F can be expressed as Cpg T03 minus Cpa T02. T03 and T02 are known quantities. In general, while here it is given, but in general while solving a problem, how will it be known? So, always we should think from practical perspectives, actual problems. So, T03 is the turbine inlet temperature, is a design parameter, is already given, fixed. T02 we will calculate from the compressor calculations, we will get the compressor outlet temperature. So, both will be known, Cpg and Cpa are of course known. Combustion efficiency is also a design parameter, means it depends on how will the combustion happen, which is considered to be a known quantity at this level. Calorific value of the fuel also is a known quantity, this minus Cpg T03. Okay. So, everything is known here. So, if you put the value, you get 0.0299. Okay. So, this is the fuel air ratio around 0.03, which is actually quite high for a typical gas turbine. So, this is coming to be around 1:33.33, which is generally considerably higher as compared to what would be used for a very lean mixture. Okay. So, the heat addition also can be calculated. Here we should note that the overall mass flow rate is not given. So, any calculation has to be per unit mass flow rate of air. So, per unit mass flow rate of air, heat addition Q in is equal to, we can directly either calculate from the calorific value F and eta B, or we can calculate from the temperature change, and you can compare both of these. I will just take one of the approach, I will use 1 plus F Cp of gas T03 minus 1 into Cp of air. I am writing 1 to denote that this is unit mass flow rate T02. This also should be can be calculated directly using eta B F Q C V, okay, which should be the easier case. Just for illustration, I have calculated in a different way. So, 1170.41 kilojoule per kg of air. Please do the calculation yourself by pausing and just verify that you get also similar solution. Okay, so, this is the heat input. So, all these small problems are like part of a realistic say design problem for a full cycle. Okay, so, I am illustrating each of these variations by designing some small problems which are specified or which are valid for this specific type of variation which are involved. Okay. So, before we end the class, we need to define two further parameters. These are gas turbine performance parameter. Till now we had considered for ideal cycle performance parameter like net work output or net specific work output and the efficiency. Okay. So, now efficiency we will define in a more accurate way in terms of the calorific value of the fuel, the amount of fuel added and the net work output, and we will define a second parameter called specific fuel consumption. Okay. So, let us start with specific fuel consumption, SFC. So, what is this specific fuel consumption? This is the amount of fuel consumption per unit amount of net work which is produced. Okay. This is equal to the amount of fuel that is needed, okay, per unit work produced, or in other words this can be written as net power output So, mass flow rate of fuel by net power output. This can also be written as F by W net. So, fuel air ratio by W net, by dividing both the top and the bottom parts with m dot A, we get this value. Okay. So, units for this are, if I just directly write in terms of SI unit, this will be kg per second, m dot F is kg per second per kilowatt, okay, of power. But it is, this generally results in a very small value. So, it is, and a more practical value is to write in terms of per hour. So, that comes out to be equal to 3600. So, because there are 3600 seconds in an hour, 3600 F by W net kg per hour per kilowatt. So, per kilowatt of power output or per kilowatt of power output, how much fuel will be required per hour, okay, per kilowatt of fuel output. So, this is a very important term. So, if I have a turbine which generates say 100 kilowatt power, okay, and we want to run it for some say like say 10 hours. So, by using this value we can directly calculate or estimate what is the amount of fuel that will be required. Okay. The second parameter of course is known to us in a more simplified form, which is the thermal efficiency. The definition is still same, because ultimately thermal efficiency is based on thermodynamics. So, the thermal efficiency of the cycle is the actual power output from the cycle. In this case, this will be, if it is written in terms of per unit mass flow rate, this will be, or let us write in terms of actual power output. Considering all the losses, everything, ultimately whatever is the net power output from the plant divided by the mass flow rate of fuel into calorific value. This is the maximum amount of energy which could have been released, m dot F into QCV. If there was complete combustion, there was no losses, nothing. So, theoretically this is the energy that is available. Of course, there is a upper limit to how much of it can be converted to work based on the Carnot cycle efficiency, but the actual efficiency we will get will depend on the actual work output. So, this can also be written as, by dividing both top and bottom by m dot A, it comes out to be equal to W net by F into QCV. Okay. So, this can also be related to SFC. So, this is also equal to 1 by QCV into SFC, okay, in terms of the SI units. So, with this we finish the discussion today. So, these last two parameters, SFC and thermal efficiency, are very important parameters for a practical gas turbine, and when we do analysis of gas turbines, we will be focused with calculating the value of these parameters. Okay. So, to summarize what we have studied today, we have analyzed the effect of the last three types of differences: mechanical losses, variation of mass flow rate and combustion inefficiency, and finally, we have discussed two performance parameters, the specific fuel consumption and the thermal efficiency. Okay. So, these are the references, the books that we are following. With this, I thank you, and we will meet again in the next class. Thank you.